This one so that it's getting recorded. Okay, so first of all, I would like to thank Claude and Jim for inviting me today and for giving an overview of our models on carrier transport. So I will not speak on alloy fluctuations and on disordered systems, but I would like to give you a little bit insight about non-equilibrium and semi-classical equilibrium carrier modeling methods and how they work out for these III-nitrate systems. First of all, I would like to acknowledge the contributors to this work. The non-equilibrium Green's function method that I will show actually has been developed first by my PhD student at the time at ETH Zurich, Sebastian Steiger. And now in the group in Kassel, Celo Andreev and Akshay Shetbalkar have continued developing this. So the semi-classical models are mostly developed by Friedhard Römer in my group. Okay, so what would I like to show today? I would like to follow up on what has been discussed yesterday actually on the drift diffusion models and how we can actually use this so-called Van Roosbroek system in quantized or nanoscale systems where the potential varies on the nanoscale. I think that's sort of a guiding idea that I would like to discuss. And I would like to compare this with a quantum transport approach, which is called non-equilibrium Green's function, and some validation and some examples. So as a motivation, we have been interested historically in transport of charged carriers in nanostructures. And I've put on two kind of historic examples of what we've been working on. So at the time, we had multi-quantum well systems with different colors, and these were put into SLED devices, superluminescent LEDs. And we were asked, so can you produce with a multicolor quantum well system a Gaussian-shaped emission? And we were trying to calculate this, which was a great challenge because electrons and holes, they populate these quantum wells differently due to their capture probability into the wells. And here you see an example that was not a Gaussian-shaped emission, but what I found was more interesting. At low current, this system emits at 1320 nanometers, at high current at 1280. So you very nicely see the rearrangement of carriers dependent on the pumping current. And actually, we could simulate that pretty well. The blue lines and red lines give that comparison. So that sort of sparked our interest in studying these multiple quantum well systems. I should say that this is an indium phosphide-based system, so it's simpler than what we are talking about now. Now, a second motivation is carrier dynamics in lasers. So if we modulate lasers directly, multi-quantum well lasers, we see that if we add more quantum wells, that to a certain degree, the threshold current density scales, so it goes down, but the modulation frequency does not scale. So if we modulate a few gigahertz, a semiconductor laser, we see that the quantum wells actually form a capacitive load, and this capacitance, it actually needs to be included if we want to understand whether actually carriers contribute to the differential gain or not. So this is a dynamic effect that validates looking at these nanostructures. Of course, as you have seen in the last 1.5 days, with III-nitrates, the story is much more complicated. We have these polarization charges, we have much deeper wells, and the question is, how can we use standard carrier transport models in order to design valid devices? And now if you go one step back and ask yourself, so what carrier transport models do we have? Now Claude yesterday said that in a semiconductor crystal, we actually have these Bloch waves, and which is correct, and a Bloch wave is infinitely extended. Now if you think of, if you put an electron into such a semiconductor, does it extend infinitely? And the answer is no, because what happens is we have finite temperature and we not only have one electron, but we have many electrons. So what will happen? This electron will of course populate Bloch states, but after a certain distance it will scatter with another electron or a phonon. And this is actually what guides the transport. We do not have ballistic devices where you have no scattering and the electrons just rush through the semiconductor, but we need to look at scattering. And what scattering does is actually, it rearranges the momentum and the phase. So we have momentum and phase relaxation processes that need to be taken into account in order to understand transport. And I've put on here a scale. So this is the sort of interatomic scale. Then you have the nanoscale and the microscale. And so this mean free path is in the order of a few nanometers. So this relaxation at room temperature really happens on that scale. And if you look at the models that we have at hand now, there are the quantum transport models like Wigner functions or non-equilibrium Green's functions, and they track actually the phase and the momentum of carriers in the semiconductor. Now, if we want to get rid of this, then we have these drift diffusion and hydrodynamic type of codes that we can apply with all the advantages and disadvantages. Just to move on, now if we look at how to include this scattering in a carrier transport model, then the classical equation is actually the Boltzmann equation, which is a gas equation. So Boltzmann in 1872, he derived that for gases and for collisions of molecules and atoms in gases. And in fact, the semiconductor people have taken that up. That was Van Roosbrück in the 1950s for germanium, actually, at the time. And he said that basically we can use that equation which tracks carrier distribution over time and under external forces. And the right-hand side is the scattering. So what we can do now with semiconductors, we can say, well, let's include all the scattering we know about on the right-hand side. So the quantum mechanics, they enter here. And let's use the band structure with the Bloch waves in order to solve this equation. And this is what can be done actually with Monte Carlo methods or spherical harmonic expansions. It's quite an expensive process in terms of computation. But the mobility versus density, mobility versus electric field that we were discussing about yesterday, actually they can be derived by Monte Carlo methods in theory. Now, a simpler method is if we expand these moments into low order in energy or in K. And then we can derive the drift diffusion or the hydrodynamic models. And however, the approximation we make is really that the carriers are in equilibrium. So the carriers, once they're excited in phase space, they need the mean free path in order to relax to equilibrium. And this is where we started thinking about if we have a quantum well system, for example, then the extension of the quantum well is actually smaller than this mean free path. So if we use brute force drift diffusion, we cannot be sure that we have actually local equilibrium of the carriers because the geometric extension of the potential is smaller than the mean free path. And so what we did and what actually Carl Hess in the 90s at University of Illinois started working on was we separate the energy space into a confined energy region and an unconfined energy region. And we say, well, these regions which have a dimension smaller than the mean free path, we treat like with a phase coherence. So we say we can solve Schrodinger equation in here and derive an envelope wave function that actually describes the carrier distribution. And here in the continuum, the carriers can move according to their semi-classical picture. And this is what we implemented. So here you see this Van Roosbrück system, the drift diffusion system. Locally, carriers can scatter into the wells. And very nicely, we have a confining potential here. So we can use a closed Schrodinger system and solve right now. Yeah?
So when you say it's out of equilibrium, it's not at equilibrium. You mean not at equilibrium with the lattice temperature? Or because is there an internal equilibrium?
In terms of equilibrium, I mean the Fermi-Dirac distribution. So the carriers do not obey.
Not internal, not even local, with their local electron temperature. It's not even that.
No, it's the Fermi-Dirac distribution. We do not include temperature. Correct. So, for these bound electrons and holes, we can actually calculate some sort of closed Schrodinger equation. Currently, we do it with a 6-band K dot P in order to include the strain effects and, the subband spacing that changes due to strain and carrier interaction. And now, in order to populate these states, we include a very simple formula, which includes carrier and carrier phonon scattering that just fills up the wells and can depopulate them. And with this model, we have been actually able to calculate the curves that I've shown for the SLED before and that I've shown for the laser. So what we can do is for indium phosphide, gallium arsenide based devices, we have a pretty good handle on calculating the electro-optical properties. I should say that, this tau here, it's the scattering time actually. This needs to be determined by comparison with, for example, small signal modulation of a laser. This is in the order of picoseconds, this time that we have here. Okay, now the question is, can we apply this to III-nitrites, to an LED? And if yes, what happens? And we saw that this was not very successful. And we had discussions yesterday about tunneling currents, about the turn-on voltage. So there are challenges. And I'm not even talking about the alloy fluctuations, right? So what we did is we studied certain updates to this model and refinements so that we can look at the experimental findings that have been made. And one thing that we started with in 2012, we actually proposed that if we have an Osha process, which was under discussion for the troop at the time, then the recombination of carriers produces a high energy third carrier. And we said our method in separating the energy space in bound and unbound states is ideally suited to say, well, this third high energy electron, it's kicked out of the well. And if it's kicked out of the well, to a first degree, it cannot contribute to the recombination anymore. So we added this rate actually to our code, and we said a certain percentage of the Osha electrons and holes do not contribute to the quantum well physics anymore. We called that Osha expulsion. And actually, when we compared the efficiency versus current data, now these are LEDs at the time from Osram, actually, blue and green LEDs, single quantum well, so no multi-quantum well physics in here. And then you see, if you include this Osha leakage, then we can match the experimental data with much lower Osha coefficients. So we can reduce the Osha coefficient by a factor of 2, actually, and we get much closer to what Chris van der Walle just said, the theoretical results that had been published with these multi-phonon processes. So this is one thing where we saw that we need to refine this drift diffusion model in order to understand the III-nitrites. Now, a second point is in the multi-quantum well physics. So this is, I think, a blue multi-quantum well LED, where we just calculate the band structure at a moderate current, and you see the Fermi level drops with each well. So this means you lose a lot of electrons from well to well. So here the electron population is lousy, so to speak. This does not coincide with what you see in experiment, because you can actually add wells and get higher luminescence. So we were asking ourselves, so what's wrong with our model? And of course, what also has been discussed, the electron sees a very high electrostatic barrier here. And tunneling would be something that is not included in this classical picture. So we just included also an effective potential correction, but here only for the continuum carriers. So we say the well is still a sharp potential and a sharp scattering center, but this little, this little barrier we have up here is subject to tunneling. And we took an implementation from Dave Ferry, actually, from 2002. And this is quite an intuitive approach. He said that the electron, quantum mechanically, is actually a Gaussian function. You can approximate it by a Gaussian function. If you take the interaction of a Gaussian function with a local potential, then you can do a convolution, and this convolution gives you an effective potential. So this is heuristic, but it works. So you get, this smoothed out potential, and you can see that now this scaling of the multi-quantum well that I was talking about actually works. And we also compare. Yeah.
But we know that the interfaces are not abrupt. So instead of calling this like a phenomenological treatment, maybe this is just reality of what potential is.
I agree. I mean, in reality, you do not have a sharp hetero interface. So you could also say this correction is due to a smoothing out of the interface.
It's not a correction. It's a correct description of the actual material.
I think I would leave this up to the growth people to discuss how sharp their interfaces really are.
They have atom probe data that show the interface is fairly diffuse.
It's up for discussion tonight.
Thank you, Claude. So anyway, we see that the multi-quantum well scales very nicely, and we again compared this to data from Osram. So what they did is they made a multi-quantum well LED with color-coded quantum well. So here you have 4 blue quantum wells and 1 cyan quantum well. And what they compared is the luminescence in the blue divided by the luminescence in the cyan. And they switched the position from 1 to 5 of this color-coded quantum well. And you see here the experiment at 300 Kelvin, and here is the simulation that we got. And if you do not include this quantum correction, actually the ratio between these luminescence data is wrong. You simply don't get it. So we believe that also with the multi-quantum well physics, we have a good handle now.
I see
Yeah.
the words photon recycling. To what extent is it important?
Oh, yeah. Actually, I skipped that, but I'm happy to explain. So at 200 Kelvin, we see a bigger difference, and we believe this is due to photon recycling.
There's absorption by the cyan from the blue.
Yeah.
It's quite a small cross section, isn't it?
True. Again, we believe.
No, the correction is quantitative or just qualitative?
Which correction?
So when you correct for photon recycling?
We do not correct for photon recycling. This is why we have this big difference. Yes. At 300, there's no correction.
So this is a computed photon recycling effect?
No. We believe that in experiment, we have photon recycling at low temperature. In the simulation, we do not have the photon recycling. This is why we have a big difference of the results.
So do you have any way to believe that the size of photon recycling?
We do not know. Yeah.
Yes, that was Richard. He doesn't believe, I do not believe. Okay, continue.
You said that you make a convolution to obtain your effective potential. So the sigma of your Gaussian is a fitting parameter of your.
Yes, it is. Okay, so due to time restrictions, I will not go into the dopant activation model, but I will switch to the non-equilibrium model. So we were wondering, how good is this drift diffusion model with all these updates, really? And now the best test one can do is to use a full quantum model, or try to use a full quantum model for carrier transport. And the non-equilibrium Green's functions method is something that could work with this. And here I've written down a little bit of history. It goes back to Keldysh in the 50s, 60s actually. And the work on semiconductors started with Gerhard Klimek in the 90s, who developed a simulator for resonant tunneling diodes, where this ballistic transport was important in order to explain the physics behind. And now we started in 2007, 2008 to apply this to LEDs. So what's the basic idea? If you look at a Schrodinger equation, then it's an eigenvalue equation, and there's no current flow for infinity, so you have full coherence. you have closed boundaries, or you can also take periodic boundaries, but in any case, you have a closed system. Now, this does not include any transport and loss of coherence. So what Keldysh actually proposed was that one can add self-energies, complex valued self-energies to the system in order to include scattering and contacts. So we make an open system out of this closed system by adding contact self-energies and scattering self-energies, and we include a broadening on the right-hand side. Now, if you look at this equation, in order to solve this, we just need to invert this one, then we get psi. And this is exactly a Green's function problem, right? So this is why this is a non-equilibrium Green's function system, which includes the tracking of the phase and the momentum of quantum mechanical carriers under the influence of scattering and open contacts. Yeah.
The scattering self-energy is here as a logical parameters, or there are some...
I'll talk about scattering in a few minutes. Okay, now we implemented that method. So again, the Green's function is actually the inverse of this bracket on the left-hand side. And all we need to do, again, is to invert this one. And we actually implemented this for a layered structure. So in optoelectronics, we have this epitaxial structure and solve it in 1D in real space. But of course, we have K-space that we also need to track. In terms of the scattering, we include the electron-phonon scattering, ionized impurity scattering, and those are mainly based on Fermi's golden rule. So you know, the coefficients, the matrix element, and the processes are derived from Fermi golden rule. Then the electron-photon scattering, I will show on the next slide what that is. Then also carrier-carrier scattering. So you see we have elastic and inelastic scattering processes that occur in this LED included. Now, on the contacts, we actually assume equilibrium, so we inject carriers in equilibrium into the system, and then we just see what happens inside the device. These Green's functions, of course, they are quantum mechanical properties. We can, although, derive classical properties by doing a summation, in essence an integration over K-space. So we get the electron density, the hole density, we get the current, and we get the LDOS, the local density of states out of this. Now for the photon scattering, this is also based on Fermi's golden rule. We have emission and absorption. Here are the matrix elements, basically. And for our LEDs, we do not include stimulated emission or absorption. So we set this photon occupation number actually to 0, and we only have this term left, which is the spontaneous emission that we include. Computationally, this is quite expensive. So what we do is we need to solve first a nonlinear Poisson equation. Then we need to solve the self-energies, and they depend on the Green's function. So we need to invert the Dyson equation, actually, and we need to have self-consistency between those two, which we call inner loop, and they depend on the Green's function, and of course also on the nonlinear Poisson system. And unfortunately, in the nitrides, due to the fact that we have these polarization charges and the Stark shifts that are included, we need to iterate the nonlinear Poisson equation. For example, the people who are doing lasers, they are always looking with flat band potential or constant electric field. They will not do this loop of the nonlinear Poisson equation. Okay, so one downside of this method is actually that it does not include non-radiative recombination. The issue is that, for example, the Osha process is inherently a 3-particle process. And on the footing of a Green's function, we cannot include 3-particle processes. So this is one major shortcoming that we're facing with this method. There has been a proposal, actually, from the Klimek group, from the Purdue people, to include non-radiative recombination. So what they are doing is they're introducing the so-called Büttiker probes, and this is simply a self-energy, a scattering mechanism, where you take out carriers from the system, you redistribute them in K-space, and you re-inject them. And so what they do is they take the classical equations that all of you know and use those for introducing the non-radiative recombination. Of course, with the downside that it's not energy resolved, you know. So you do not really know which carriers in K-space do recombine with what kind of strength. But that's an approach that they have been pursuing. They presented that last year, actually. We have excluded these non-radiative recombinations up to now. Okay, so the first question for us was, does this code work for PN junctions and for LEDs? So this has never been tried before. And now we started out with a gallium nitride resistor. You see it's pretty small, it's only 80 nanometers wide. And we looked at the currents. If you include no scattering, so this would be the Bloch wave approach, you inject electrons and they just fly through the device, right? There's no relaxation, no scattering whatsoever. This is ballistic transport. If we include scattering, this is energy, this is X, then you see the carriers scattering to lower energies and we get actually an ohmic resistance, so to speak. And now what we did is we used the scattering mechanisms that we have at hand and tried to calibrate them with comparing with experimental data and with Monte Carlo data. So here you see hole mobility versus concentration from experiment for gallium nitride. And we tried to choose the scattering mechanisms so that we get similar mobilities. So here you see the GF light is actually the Green's function method. So you see we tried to get similar mobilities to what we see from Monte Carlo results or from experiment. And the scattering mechanisms, again, is carrier-carrier, then carrier ionized impurities, and carrier phonon scattering.
What temperature is this?
This is room temperature.
The low carrier concentration mobility is,
This one?
well, anything more than about 30 is unbelievable.
We got it from there. So maybe it's low temperature. I don't know.
Yeah, it's not believable.
Okay.
I
In-
think 30 is kind of the highest number that's ever been believable at room temperature.
Okay, in any case, if we look at high densities, so we're somewhere here, we should be much lower. We are aware of this. But in that case, if we have strong scattering, we will not get convergence anymore. So that's sort of a trade-off we are working on. I agree. I mean, even with these red dots, we should be much, much lower.
Yeah, it's just not believable.
Yeah. Okay, so in the next test, we looked at a PN junction. And we already have discussed yesterday what drives a PN junction. And it's basically the minority carriers. And so you have two cases. You have a long base case where actually all the minorities recombine in the minority region, or you have a short base type of description where the carriers mostly show up as minority currents at the contact, right? And so we were curious, do we have a short base or a long base case for the NEGF? And now here you see this gallium nitride PN junction, and we get here the short base, the long base, and here the NEGF. So it's somewhere in between. Unfortunately, what we saw is that at the contacts, the carriers do not have an equilibrium distribution yet. So we still have hot carriers included. This is what skews these data somewhat. And if we look at the carrier densities, it's the same. So the dashed carrier densities come from a drift diffusion solver, and the solid lines come from the NEGF method. So we're somewhere in between the long and short base regime, which kind of made us happy because we saw we have realistic results for this type of PN junction.
So what are your minority carrier diffusion lengths?
The minority carrier diffusion length is basically very large because we do not have non-radiative recombination, and most of the carriers go to the contact.
Okay, maybe I'm misreading your graphs. That's not what it looks like.
Okay, it's carrier density. This is the P region. This is the N region. Now this is the intrinsic region, and we get these carrier densities at the contacts.
Okay.
And you know, this carrier density is actually driven by the recombination property of the contact itself. And actually that was not, we were not very happy about this, because the contact influences how the device works. And you're absolutely right, in reality, the minority actually region should decide on the minority carrier diffusion length. I agree. So what we did is, we could not make this any longer because the simulation time is already prohibitive. So we did a trick, and this trick was that we introduced minority barriers. And the minority barriers, we just said, well, let's just introduce an artificial heterojunction, reducing this barrier actually reduces the carrier density artificially so that the contact is decoupled from our quantum device. And that way, you know, you can introduce a minority diffusion length here and translate this diffusion length into an energy barrier. And that's what we did in order to decouple these two from each other, and that way get realistic minority carrier diffusion length. Okay, now, yeah, we did that, and you see actually that with minority blocking, we get realistic minority carrier densities, and it only drops very sharply down to the contact. So that we were also happy with. Now, the interesting question is now, how about a single quantum well diode, LED? And we looked at an N-P structure with one quantum well in there. Well width is 3.4 nanometers. We have barriers of 10 nanometers. And you see the contacts, they are rather small, only 15 nanometers. So they are pretty short, actually. But again, such a simulation takes, the IV curve takes around 1 week on a multi-processor computer. So this is what we could actually do. And we started looking at the IV curve and at the carrier density. And what we saw is that if we use the standard drift diffusion solver, the turn-on voltage for such a diode is between 2.9 and 3 volts. If we compare it to NEGF, we get a shift of 200 millielectron volts. And we saw that this is due to tunneling. So if we turn on the diode, then we get an electrostatic barrier here, and actually carriers can tunnel through this little barrier and go into the quantum well, and this decreases the turn-on of the diode. Now you can discuss again. If the interface is not sharp, then you don't get that tunneling, but you get an effective barrier lowering, of course. So, you know, you can again discuss what really drives the turn-on voltage of this diode, but if you assume sharp interface and include tunneling currents based on an NEGF method, you get a reduction by 200 millielectron volts. Then we looked at the spectra, the radiative recombination spectra, and so the dashed lines are the NEGF method, and again the solid lines is a drift diffusion type of method. What we saw is that towards the band gap we get a much larger, smaller slope, and this is because of the Obach tail that's included in the simulation. The tunneling of carriers into the band gap. So that's naturally included, of course, without any fluctuations, you know. And what we also saw is that this depends a lot on the discretization we do in energy space on the band gap, but again, the effect is included. Also, the amount of radiative recombination is similar to what we see in the drift diffusion simulation, and that we compared a little bit more in detail. Now, what we did is we took the carrier densities that we have in the active region and actually extracted a B coefficient. So you can say, well, the simplest model is B times N times P, And so if you have N and P, then you can extract an effective B, so to speak. Of course, that's not energy resolved, not K-space resolved, but it gives you a rule of thumb, so to speak. So this is the B that we extracted out of this exercise. And you see that around the quantum well, the B is in the order of 0.6 to 2 times 10 to the minus 11 cube centimeter per second. And typical drift diffusion models, you use numbers like this. So it's quite comparable, and we can also be actually confident that the radiative recombination model works in this method. Okay, then the final test was to look at a multi-quantum well LED. And we have wells with 30% indium content, which is towards the green. And we have 2 quantum wells here with a thickness of 3 nanometers again. Then we have PN, also pretty short regions. We have an argon electron blocking layer. And we calculate the carrier density inside this system. Now first, it's interesting to look at the local density of states. Now here you see the conduction band edge, valence band edge, and the local density of states at k equals 0. Now what you recognize immediately is the bound states. So here's the bound electron state, here's the first state, which follows the wave function you normally have. Although in the bulk you see the nice square root type of behavior, so that makes sense. However, interesting is here the barrier region. We see resonance states here, and we see a strong resonance state in the barrier between the wells. For the holes, you see roughly the same. You see the ground state, you see the excited state. And now it's interesting that this state in the barrier actually contributes to a lot of tunneling current. So if we track the current, then we see that electrons get injected. They hit the wall here. Red is actually negative current, blue is positive current. They get injected, they hit the wall here, and then they redistribute in this 2 quantum well system. So that's what NEGF tells us, that actually there is, number one, there's tunneling, and number two, there's redistribution of carriers due to this wall or this interface that we have between the gallium nitride and the aluminum gallium nitride. Yeah?
Does the NEGF give you the in-plane K dispersion? Do you get the in-plane K dispersion, parabolic dispersion?
Yes, it does. However, we assume parabolic shape.
What about for the barrier state? What is the in-plane dispersion?
It's the same.
So it's also parabolic?
Yes, yes.
In 2D? In the in-plane direction.
Oh, in in-plane direction, here you see the density of states. Yeah?
You have considered the barrier 5 nanometer wide. What happens if the barrier will be thickened? For instance, 10, maybe 12 nanometers.
We have not looked into this.
Is the tunneling so effective?
We have not looked into this. But you can see that the tunneling is mainly through this spike on top. So my guess would be, yes, you still have this tunneling. So then the final interesting question was, this is the current. Let's look at the carrier density. So we can plot the energy resolved carrier density as well. And what we saw is that I have made 3 cuts now. 1 cut through the p-side quantum well, 1 cut through the n-side quantum well, and 1 cut through the barrier. And the solid lines, they are actually Fermi-Dirac equilibrium distribution functions, and the dashed line is the NEGF result. And what you see very nicely in the quantum well here and here, you have equilibrium distribution, but in the barrier region, so above 3.5, 3.6 electron volts here in the barrier region, there's a strong imbalance, deviation from the equilibrium carrier density, and meaning that we have a higher carrier density than what equilibrium distribution would suggest. And this actually was a nice confirmation of our drift diffusion model, now I go back to the semi-classical model, that actually separates the two energy regimes from the bound and the unbound regime, and we can actually have an independent continuum carrier distribution that can pile up carriers actually if the recombination in the wells is not strong enough. Because what we have here, again, we do not have non-radiative recombination. So meaning the recombination in the well is basically less than what we would expect in a real LED. Okay, so I think I still have time, right?
10 minutes.
10 minutes. Oh, great. So I go back to the part where I wanted to explain the doping, because I know Sergey is quite interested in this. So if we look at the classical model now and look at the magnesium dopant issue, then we learned that the magnesium activation energy is quite high. And within the model we are using, we can include a Shockley type activation. So this means that at room temperature, not all acceptors are activated. We have this activation rate, or dependent on the activation energy. And of course, we can also saturate the states. So if we increase the hole density locally, then the activation goes down. And now what we did is we tried to include two effects. One is the Poole-Frankel effect of a local electric field, and one is this proximity effect that we have. The proximity effect, if we have high acceptor density, then we have an effective reduction of the activation energy. And this has been published actually experimentally. Now here you see magnesium in gallium nitride, acceptor ionization energy versus concentration. And what you see is if the acceptor concentration goes up, then the activation energy goes down. And we believe this is important to include into a simulation to get a good handle on how the actual free hole density is. Now on the right-hand side, you see the donors in argon and emission rate versus voltage. This is basically the Poole-Frankel effect. And we have taken experiments from this paper, and the solid lines are actually our model that we have developed for this. And now you could say, why am I talking about this? And what we found is that one decisive factor is if you have, I try which one of this works, if you have a p-n junction, then if you inject electrons, then these electrons, they actually see an electrostatic barrier here. Now if you make an active region, this is conduction band, this is valence band. You see an electrostatic barrier here. If you make a recombination center like a quantum well here, then the electrons, they recombine nicely. Now this electrostatic barrier, it depends strongly on the depletion and the depletion actually of the dopants. And now what we see is that if we take a single quantum well LED and with p-n region and an electron blocking layer, and if we grade the magnesium concentration here, then we see that dependent on the local carrier density, if we turn on all these activation models, then you see if you put in, now I don't have a scale here, but if you put in 2 times 10 to the 19th of magnesium, you only have high 10 to the 17th of activation. But what you see is actually that here it trails off the higher the current is. Because of the saturation with holes, the acceptor states get saturated and the ionized impurity density goes down. So this means if the ionized impurity density goes down, you reduce this barrier, which introduces leakage. So if you do not engineer the magnesium profile on the P side correctly and take a pretty sharp profile, then you introduce a lot of carrier leakage, even though you would have an electron blocking layer. And we showed that, you know, if you compare now the current contributions to the LED, that again, if you have like 1 over x or 1 over x squared profile here, only around 10 to 15 nanometers, that the leakage current increases to a level where it actually correlates with the Osha current. So again, activation of magnesium is an important model that needs to be included in order to get the electrostatic barrier around the quantum well correctly. So now I'm at the end. Thank you very much for your attention.
So picking up on this last issue of dopant activation, I don't know whether your models can address this, but there is this mystery, at least in my mind, about gallium nitride LEDs operating at 10 Kelvin.
Okay.
Because there is almost no activation of magnesium dopants at such low temperatures, you would expect that you couldn't get any current through the p-type region. So do your models shed any light on this?
Okay, the question is, what's the underlying mechanism that causes this luminescence? If it is some kind of tunneling through the magnesium states, we have not included that. But I don't know, we could try that, you know, just run the code at 10 Kelvin and see what happens, yes.
I was actually wondering, when you showed those results at 200 Kelvin, where you said that you needed to include photon recycling, I was wondering whether the discrepancy with the experimental results might have something to do with that, but I'm not sure.
Mm-hmm.
So your leakage calculations are intriguing. When you're looking at the fully biased diode, are you looking at the applied bias across the junction and comparing it to the built-in voltage of the whole junction? Because fundamentally the barrier has to be, you have to scale this to the dBi.
That's right.
Yeah, and today's LEDs at very high current densities, say blue, dBi is 3.3 to 3.4 volts. The LEDs are working very well at say 2.8 to 2.9 volts.
Yeah.
And with the CBO-VBO ratio, you're looking at 0.2, 0.3 eV.
Yeah.
dBi minus just in the conduction band. So I think there's a very large barrier there. Fundamentally, just comparing the external bias, well, just the junction bias compared to VBI, the built-in voltage of the junction.
Yes, I agree, but you only have a built-in voltage if you have depletion. If you have perfect depletion. And the message here is, if you do not activate the magnesium, then you do not have perfect depletion at that site. I agree with you. But if you only have partial depletion at this very location, then you have this voltage drop, but you do not have it at the right position.
So you're saying that depletion is going deeper?
Yes, yes. And in fact, I was happy to see that I think Sora or UCSB, they published an LED without electron blocking layer at some point. And this was exactly what you guys did. You removed the electron blocking layer and used the electrostatic barrier on that side to block the electrons. And we did that calculation actually, and we were happy to see that it matches. So you proved it basically.
Thank you.
Okay, if nothing else, let's send the speaker again. No?
So just a comment on what I said about photon recycling.
Yeah.
To have efficient photon recycling, you need two things. You need first that the photons indeed stay inside your material to be recycled.
Yeah.
And second, the quantum efficiency and a large fraction of those photons is reabsorbed, which is not obvious. So that's the second thing. And the third thing is that the quantum efficiency is not high enough to indeed have an effect.
Yeah.
So it's not so clear for me at first sight in those conditions. So
I just can say we do not have proof that the sole reason is photon recycling. I tend to agree.
I'm just saying with a proviso.
Yeah.